Kia ora Year 11 and 12. This is question 7 from the revision sheet. Probably best to watch question 6's video first, or make sure that you've gone through that question, because they're very similar. So I'll probably go a little bit faster in this one than in the last one. Okay, so let's read it through. We've got a circle and it's got a radius of d. Okay, so there's my radius there. Oops, there it is. And it's got a chord from A to C. Now this time we're told that the length of the major arc ABC is 30 centimetres. So let's just check we remember what a major arc is. So that means it's this one here around the outside. Gone a bit wobbly. There we go. And that's 30 centimetres long. Now that's not a big drama. We just need to make sure that we use the arc length formula properly. Okay, and my arc length formula is S equals R theta. So let's think about what my angle is here that's forming that arc. Well, I'm going from the centre, and it's this angle all the way around here. So we might as well think about that now. If we've got beta as my angle here, this is the rest of the revolution. Now when you're in year 9, you remembered that angles at a point add up to 360 degrees. Right, so we know that in degrees it's 360 take away whatever that angle is. But because we're working with circular measure, we've got to do that in radians. So the angle that we're interested in is 2 pi minus beta. Okay, whenever you're working with circular measure, you must be in radians. So we can write down here that we've got 30 equals R, which is D, times 2 pi minus beta. And we're just going to park that and come back to it, because what we're asked to show is if the shaded area, which is this segment here, is equal to 1/12 of the area of sector OABC. Right, so remember the sector is going to be that area there. Then we have to show that the value of D is equal to this thing here. So we're going to start again by writing down what we know, and let's do that now. So area of segment. So first we put the formula, and then we substitute in what's right for us. So the area of a segment is half r squared times theta minus sine theta. In our case, that gives us 1/2 d squared, and my angle is beta minus sine beta. So notice that I'm working with this segment here, which is being formed, wow, what a big mess, by that angle there. So that's why I'm using beta, right? Not 2 pi minus beta or anything weird. So that's that one. We'll call that area 1. And now we've got the area of a sector. And that's half r squared theta. In our case, we can substitute in, so it's 1/2 d squared. And what's my angle? Well, again, I'm working with a major sector. So the angle I need to work with is the one that's going to give me all of that there. And that's going to be 2 pi minus beta. Okay, and that's fine. It's not a problem for the area of the sector or the arc length formula to work with angles that are greater than 180 degrees. If you think back to when we proved where those formulae came from, that proof still makes sense, right? We're dealing with a fraction of the circle which is greater than half. So we're all good. So this is area 2. And now we're going to write an equation that links those two things. And that'll be on the next slide. So we know that the shaded area, area 1, is 1/12 of area 2. Okay, so 1/2, what have we got? 1/2 d squared times beta minus sine beta is equal to 1/12 times area 2. And that's 1/12 times 1/2 d squared times 2 pi minus beta. So you can see why I said to watch the question 6 one first. The process from here is quite similar. I'm going to divide through by a common factor, right? So we can get rid of the 1/2 on both sides, dividing through by that. And I'm also going to divide through by d squared. Now, sometimes dividing through by things, you've got to be really careful that you're not accidentally dividing through by 0. But we're safe in this case because we know that d is the radius, and we can't have a radius of 0, or else we just have a point and not a circle. So that's all good. So what have I got? Well, I've got beta minus sine beta equals 1/12 of 2 pi minus beta. So I look at that, and now it's time to take a look at what I'm trying to show. And what I want to show is that d is equal to 5 over 2 beta minus sine beta. So before I start going too much further, I look at that and I go, well, there's something I notice in there is I haven't got any 2 pi's. And I haven't got d in that equation anywhere. So we do what we did in the last question, and we say, well, what links d and beta? And the link comes from this. The arc length of that major arc was equal to 30 is equal to d times 2 pi minus beta. So I'm going to rearrange that formula, and I'm going to get 30 over d is equal to 2 pi minus beta. I'm going to take this equation and I'm going to substitute 30 over d for 2 pi minus beta. And that's going to help a whole lot because I'll now have an expression with d and beta in it. So it'll go like this. b minus sine beta is equal to 1/12 times 30 over d. So now we're getting closer. We're going to clean that up on the next slide. So b minus sine beta is equal to 30 over 12d. Simplifying the fraction, we can take out a common factor of 6, and we get 5 over 2. Now remember, where I'm trying to go is to show that d equals 5 over 2 beta minus sine beta. So you can see that I'm nearly there, right? Cross multiplying, I'm going to pop that into a bracket. We get 2d times beta minus sine beta is equal to 5. And now I get d is equal to 5 over 2 times beta minus sine beta as required. Okay, so if you need some more practice at easier questions on the area of a segment or a sector or a triangle, remember chapter 12 of theta has got the area of the circular measure stuff, and chapter 9 for the area of a triangle. Thanks for watching.